Hello, my name is Terry Soul, and this is Programming Chaos, a series of videos on interesting projects that are useful for beginning and intermediate programmers to use to hone their programming skills. Today's video is on diffusion limited aggregation, which you can see over here. Diffusion limited aggregation is a model of a physical process in which we have particles moving around randomly. That's the diffusion part. And then aggregating, sort of sticking to a fixed structure. And so that's going to be what we're programming today. It's used to model physical processes and also can be used to generate very interesting sort of procedurally generated structures in art, as we'll see. Okay, so to begin the coding, what we need is a set of particles. And so I'm going to use the same code that was developed in an earlier video on swarms of particles. If you're not familiar with that, you might want to go back and rewatch the video, but I will walk through the code from it very quickly here. So the first thing we have is our particles class. So this just defines what a particle is. And basically they have a location, they have a hue, and they have a radius. And then we have a constructor that constructs the particles, an update function that right at the moment doesn't do anything except check to see if they're off the screen and wrap around top and bottom if they are, and then a display function to display the particles. And in our main code, we create the swarm of particles, we initialize them, and then in our draw loop, we update them and display them. And so if I run this, we simply get a bunch of unmoving particles because the update doesn't have them move. And so that's the first thing that we're going to need to add for our diffusion limited aggregation is that random motion. And this is basically Brownian motion. So they're just going to bounce around randomly. And that's pretty easy to add. We simply want to go into the update and add a little bit of random noise. However, we may want to scale that noise. So I'm going to do it first by creating a variable for the amount of noise. And as with most of our parameters, you can adjust this if you want, and you'll see that you get slightly different forms. And then we can go to our update and use that noise. So there we go. We're just adding random noise to both the X and the Y value. And now if we run this, you can see the particles are bouncing around randomly. So that's technically speaking Brownian motion, just little random steps. So the next thing we need to do is the aggregation part. And so that is particles, when they get close to a particle that's already stuck or frozen or static, they also freeze. And so a few things we need to do here. We need to keep track of the status of each particle. Is it frozen or not? And then we need to check for the ones that are not frozen. Are they within a particular radius of a frozen one, in which case they will also freeze. And so I'll begin with that status, just by adding another variable to our class, which tells us whether or not a particle is frozen. And we'll begin by setting in the constructor frozen to false. So all of the particles will start unfrozen. And then as part of the update, we'll check to see whether they're within the radius of a frozen particle and have them freeze. After we've updated the position of a particle, if it's not frozen, then we'll check for freezing. And I don't have a check freezing function yet, so we'll need to rewrite that. We'll need to see how close this particle is to all of the other particles, and in particular, check if it's close enough to a frozen particle. So the first thing I need to worry about is how far away it is. So I'll use some variables to calculate that distance. So dx and dy will be the distance in the x and y direction to each particle, and then I'll calculate the total distance. So I'll go through all of the particles in the swarm. That's my for loop. So here I'm calculating the distance in the x direction between the current particle. So x is the particle that is running this code. It's the current object that's running the code. And then swarm I, because I goes through this for loop, is every particle in the list. So I'm checking the current particle with every particle in the list and calculating the difference in distance. One thing to note is that does mean that at some point a particle is going to be checking the distance to itself. In many cases, that can lead to errors. It won't here because if a particle is already frozen, we won't bother running this code. And if it's not frozen, it can't cause itself to freeze. So in this particular program, it doesn't matter that we're checking a particle against itself. But in other programs, it might. So for example, I've written artificial life programs with predators, and I had to be very careful. On the first pass, I made a mistake, and the predators would eat themselves because they were close enough to attack themselves. And so that's something that you often have to worry about in this sort of a model where you have a lot of particles that are interacting with each other. You get weird effects if you allow particles to interact with themselves often. Not like I say in this case, but it is something to keep in mind in other similar projects. So we'll calculate the distance in the y direction, and then the overall distance is the square root of the square of the x. That should be plus the square of the y. It turns out this is a little inefficient, and later on I'll come back and revisit this code worrying a bit more about efficiency, but this is the most straightforward way to do it. We very clearly calculate the x distance, the y distance, and then use the square root of the square to figure out the hypotenuse, basically, which is the direct line distance to the particle. And now we can say if that distance is less than some threshold distance, and I'll have to define that again as a variable because that threshold can make a big difference in how the model works. And if this particle that we're checking against is frozen, then my current particle should freeze. And notice here that, again, I'm looking at each particle in the swarm based on the variable I, and frozen is a Boolean, so that's automatically going to be either true or false. If it's true, it means the particle is frozen, the one I'm checking against, and the current particle, the particle running this code, should become frozen. And the way that we make it become frozen is simply to say frozen equals true. And the other thing we can do, this is helpful for efficiency's sake, is once that happens, we'll return from this function. So once a particle freezes, there's no point in checking against the rest of the swarm. So let's say I'm looking at particle number 3, and I'm going through and checking against every other particle in the swarm, and I get to particle 8, which is frozen, and 3 is near it. 3 now freezes. There's no point in checking against the other 900 plus particles in the swarm. My current particle is frozen. I might as well return from this function. And so that's this return. Optimizes the code a bit. And then we have our threshold variable, which is an error message right at the moment because I haven't created it yet. So let me add the threshold variable. So I'm going to set the threshold to 10, and that's like noise, something that we might want to adjust in order to get the model to behave a little bit differently. Let's see. The other thing we need to do now that particles can become frozen is we only want to do the random noise if they're not frozen. So in fact, I said if not frozen, check freezing. In fact, we can put that covering all of our code. So we only want the particle to move if it's not frozen. Frozen particles, basically, we don't have to do an update on. They just sit in the same place. So we need one more piece. If I were to run this now, we would see lots of particles moving around randomly. None of them would ever freeze because we don't have sort of that seed frozen particle. So I need to add that as well. So here's where we create all of our particles, and I'm just going to pick one. It might as well be the 0th one. And I will freeze it. And also put it in the middle of the screen. So now we can run this. And there you can see our frozen particle and the other ones, as they get close enough, start to freeze. And you'll notice there's a little gap between them, and that's because I used a threshold of 10. Maybe an effect that you like, and if that's fine, great, but I think I'm going to go and make my circles a little bigger so that it really looks like they're touching. So let's do that here. So I will increase this radius to 10. And so here you can see when they freeze, they're actually touching because they're a little bit bigger. And there we go. That's the basics of a diffusion limited aggregation code. turns out there's lots of interesting things we can do from here. So as we've seen, changing the threshold changes how things look. We can change the noise, which is how much they move around. We can also do things like play around with the radius, the size of the particles. We can change the colors of the particles and so forth. So let's do some of those things. So the first thing I want to do is bias the noise a little bit, because I always find that this gives some interesting effects. In my particles here, where we're updating them, in addition to just this random noise, I'm going to add a little bit of bias, which is basically going to be downward motion. So the particles are going to bounce around randomly, but also move down the screen a bit. And then I'm going to take my initial frozen particle and put it nearly at the bottom of the screen. So let's do height -2, so that'll put it just above the bottom of the screen. So here you can see my frozen particle is down at the bottom, and it's a little hard to tell, but all of the particles have this slight bias to be falling. And so if you sort of just get a general picture of the whole screen, you can see that they tend to be falling a bit. And what this gives you is sort of almost a tree-like structure, so that as the particles fall, they aggregate onto the structure and it starts to build out a tree-like structure. And how dense that is, how long these branches are, depends a lot on the noise. So I suggest playing around a little bit with that noise function or that noise value and seeing what sort of different shapes you get. The other thing that's sort of interesting here is because the particles wrap around, when they get to the bottom of the screen, they jump back up to the top. Well, most of the particles in the middle, rather than getting to the bottom and wrapping, become stuck onto my structure, and so you'll see lots of particles over on the side and none in the middle, and that's just because of the way the particles are moving and wrapping. And what this will eventually lead to is this sort of tree-like structure, and maybe it's more like a fan coral, if you will, that forms sort of a V because all of the particles now are off to the sides. And if we wanted, we could fix that by saying, well, when the particle gets to the bottom of the screen, instead of just wrapping, we also give it a new random X position. So let me show you what I mean by that. Come back to my update, and so instead of just wrapping for Y, I'm going to do something a little bit different. If Y is larger than the height, that is to say it's gone off the bottom of the screen, I'm going to say Y equals 1, which puts it back at the top of the screen, but I'm also going to re-randomize my X value. So what this will do is when a particle gets to the bottom of the screen, it wraps to the top, but at a random location. And so we'll no longer get that sort of filtering down the middle. In the interest of time, maybe I'll put a little more bias on the downward motion, and maybe I'll increase the noise a little bit. And so again, we get this sort of growing tree-like structure, but what we're not going to see is that filtering out of particles in the middle. And that causes it to grow up a bit more than it did before, but it will also sort of grow out to the sides. And the main point here is that by playing with things like noise and how particles wrap and how much downward bias there is, you can create very different shapes. So a couple of other things we can do with this as long as we're working with it. One is to play with the color. So here I have a hue, and it always starts at 0 degrees in my color wheel, which gives me red, but I can fiddle with that, and there's lots of ways to do it. I'm going to start with one that I kind of like, which is when a particle becomes frozen, it's going to pick up the hue of the particle that it stuck to, that it froze to, and I'm going to consider that the parent particle. And so to make this work, each particle has to remember its parent, or the one that it froze to. And so I'm going to begin by adding that to our class as another data member. So each particle will know who its parent is, that is to say the particle that it stuck to. And initially, there is no parent. And so particles are objects, and a non-object is null. So null is sort of like the 0 for objects. And now when we freeze, I'm going to say the parent, which is the particle that caused this particle to freeze, is that ith particle. So if particle 3 froze because it was close to particle 8 that was frozen, particle 8 becomes the parent. And now I can say the hue of this particle is equal to the parent's particle plus a little bit. And that plus a little bit is so that we start moving through the color wheel. And again, in the interest of time, although 1 works pretty well, make the number a little bigger just so that we can see the effect quickly. The other thing that I need to worry about is the color wheel just goes up to 360, and I don't want to go beyond 360. So I'll do the classic programming trick of using a modulus. And so if I get to, say, 363, I divide by 360 and take the remainder, which gives me 3. I've basically come around past 360 and back to 3. And now when I fill, I'm already filling with that new hue, so we can take a look at how this works. So here we go. All our particles are red because they started with a hue of 0, but as they attach to the parent, they inherit the parent's hue plus a little bit. And so we're working our way through the color wheel, and as each new particle sticks, it's sticking to a particle that already had a different color, and so we get this nice rainbow effect. And how strong it is depends on how much you're adding here. I'm adding 4 so that we can see it fairly quickly. One of the things you'll notice is we get back to red eventually. We've gone all the way around the wheel, and then we start back into the oranges and yellows. And if I didn't put in this 360 modulus here, then once they turned red, they would continue to be red throughout. So that's one thing we can do with the parent. Another thing that we can change is instead of just drawing circles, we can also add lines between particles and their parent. So let's do that. And once I do it, you'll sort of see why it gives for an interesting pattern. So in the display, I want to do a line from the current particle back to its parent. The first thing we have to do is make sure that this particle has a parent. And really there's 2 ways to do that. We can make sure the particle is frozen, and if it's frozen, it must have a parent. Or a little more directly, we could just check to make sure the parent is not null. And that's a little more of a direct check, a little safer in terms of the program. So if the parent is not null, we need to add a stroke. There's no stroke for the circles. So when we draw our circles, there's no outline around them, which I think works well, but of course that would mean there's no line, so I have to do the stroke again. And I happen in this case to be doing it the same hue as the particle, although we could choose other colors there, maybe play with that a little bit as well. And there we go. Now we're just drawing a line from this particle's XY position to its parent's XY position. And if I run this, we actually probably won't see much. And the reason we won't see much is because that threshold is basically the same length as the diameter of the particles. So even if there's a line being drawn between them, we're not seeing it because the circles overlap anyway. And so if we want to see those lines, one way that we can do that is to increase our threshold. So let's make this 20. And now you can see they freeze further apart and draw a line between them. You'll also notice that the whole pattern grows much faster, and that's because with this longer threshold, particles fall within that freezing range much faster. And there, I always thought that's sort of a cool pattern. So here we have color, in a sense, being inherited by the parents. We can also do the same thing with the radius. So this is one I also think makes for a nice pattern, and you'll see a little bit of it even in my background. And the idea is to do the similar thing that we did with hue, but do it with the radius. So the hue is based on the parent. The radius is also based on the parent. And what tends to work well here is for the radius to get smaller and smaller. One approach would just be to do a subtraction, like subtract 1. The problem with that is eventually you're likely to hit negative numbers. And with processing, if you draw a circle with a negative radius, it just treats it as a positive, and so our particles will get smaller and then they'll get bigger again. If you want that, great, but it's not what I'm going for. So I'm going to take a different approach, which is to multiply by a number that's close to 1 but a little smaller than 1. And so in this case, 0.98 means each particle will be 2% smaller than its parent. And it will approach zero but never reach zero. So I'm going to get particles that are smaller and smaller towards zero but never going, say, into the negatives, which would cause them to grow again. And then the last thing I want to do to sort of go along with this is take my original particle and make it a little bigger to begin with. Let's try 15. So there we go. We start with fairly large particles, but as we move our way out, they're becoming smaller and smaller. They're assigned a smaller and smaller radius. Notice that the particles undergoing the Brownian motion have their initial radius, which was 10, but my first frozen one was 20, and so ones that connect to that are 2% smaller and then 2% smaller, and then as they go out, they get smaller and smaller, and so you have this cool sort of branching structure. And as you can imagine, from here there's lots of things you can do. You can adjust how much smaller they get. You could draw the lines in a different color. Sort of an interesting thing to do with this model that I will show, because I kind of like it, is actually to take the lines out. So I'll just comment this out for now. And while I'm at it, maybe make the threshold a little bit smaller. Let's go with 15. And so here you get the particles initially connected because their circles overlap, but as they get smaller and smaller, they freeze without the lines between them. And again, it might be an effect that you particularly like, so kind of worth taking a look at. Excellent. Now the last thing I want to do is talk a little bit about efficiency. So although our code is running pretty quickly, if you try and do this in a larger window with a lot more particles, you will see it start to slow down. And the reason for that is our check for freezing function is really quite slow. Every single particle in our swarm is checking against every other particle to see whether or not it should freeze. This is what would be called n squared time. If I have n particles, each of those n particles has to check against that same n particles, and we end up with n squared checks. And that's pretty slow. So anything we can do to speed it up is going to be helpful. For example, here we're checking to see if the particle is frozen before we freeze the current particle. But I'm only checking to see if it's frozen after I've already done all of this math. And if the particle isn't frozen at all, then I'm wasting my time doing that math. And okay, what is it? It's a subtraction, it's another subtraction, it's a couple of multiplications, it's an addition, and it's a square root. So it's about 6 different mathematical operators. Doesn't take a computer very long to do 6 mathematical operations. But if I've got a swarm of, say, 1,000 particles, 1,000 squared is a pretty big number, and if I have to do 6 mathematical operations that many times, it's going to start to slow things down. And so it's worth not doing these operations any more than we have to. And in particular, square root is relatively slow. It actually takes quite a few mathematical operations to calculate a square root, or maybe a lookup in a table, depending on how the computer is doing it sort of underneath. But in any case, it's generally an operation. We want to avoid doing it thousands and thousands of times. And so what I'm going to do is take this if frozen and make that my first check. Let me clean up my indenting here so this is a bit easier to follow. There we go. So if the particle I'm looking at is not frozen, then I'm not going to bother with any of these calculations, and that's going to save a bit of time, possibly quite a bit of time. And then we can do similar sorts of improvements by checking after we calculate each of these distances. So for example, if the x distance is already bigger than the threshold, there's no point in figuring out what the y distance is and calculating the distance. And so I can put in another if here and only bother to do the rest of the checks if my x distance is less than the threshold. And I could do a similar check with my y distance. I only want to bother calculating the total distance if y is also less than the threshold. So that will speed things up a little bit. probably won't notice it in this code as I have it here, but if you go full screen and say you want to go up to 10,000 particles, then those changes that save doing some calculations can make a big difference. One last trick that's useful here, as I said, the square root is a little bit slower to calculate, so it's nice to avoid if we can. Turns out we don't have to calculate the square root. We can do exactly the same effect by using the threshold squared. Right? So instead of calculating a square root, which is a little slow, I'll square the threshold, which is faster. It's just a single multiplication. And then I've saved a little time. I've done a multiplication instead of a square root. And in fact, if you think about it, well, this is sort of silly. Why calculate square of the threshold on every single loop? I could just do that once and make it a new variable. So I'm going to do that. I'm going to call this threshold squared, and I'll just calculate it once at the very beginning. There we go. Squared, SQRD, QRD. So this is a useful trick to optimize code. It's often not worth doing if you're only going to use this variable once or twice. But in a case like this, where I have n particles, where n is a large number, being checked against n other particles, that's, again, n squared checks. If I can save a little bit of time in doing all of those checks, that will save some time overall. Even though the savings on each check is very small, just getting rid of a single multiplication operation, I'm actually saving thousands of multiplication operations, and that can make a difference. So here we go. The code should work exactly the same, maybe a little bit faster. We probably aren't going to notice it unless we put in even more particles, but it is a good trick to keep in mind in terms of optimization. Okay, thank you.